Yeah, I'm trying to do that. Yes,
Okay.
just give me 1 second. Yeah, where is it? I'm also a little, technically challenged. So where is my? Where is it? Full screen. Can you guys see the full screen?
Yeah.
Yes. Okay, good. So.
Can I start?
Yeah, you can start. Yes.
Okay. Thank you very much, Sudeshna, for the introduction. Oh, something's going on.
Oh, sorry. Sorry, I'll do it again.
Yeah. And I'm very happy to for the invitation to speak at your institute today. And I'm going to talk about some results that I obtained with my advisor a couple years ago, but also I will talk about some very recent results that will be published. Will be published in the archive very soon. So I'm excited to give this talk. Thank you. Okay, so maybe we can go to the next slide. Yeah, thanks. So yeah, as I said, I'll talk about two things mainly. The first thing will be the exponential decay estimates for fundamental solutions through Schrödinger operators. And then the second thing is we will then view these exponential decay estimates through a different angle using a new landscape function of Marcel Pilot and Svilana Miboroda, which has been used to study Anderson localization. So then we will see some new results regarding the landscape function and also a new one for magnetic Schrödinger operators. So I'll give more details about what these things mean very soon. Okay, so in the next slide, here I at first I want to give a quick reminder of what is the exponential decay of eigenfunctions. This is a very classical problem coming from physics. In the theory of quantum mechanics about eigenfunctions to the Schrödinger operators should decay exponentially, right? So here I have a picture of how in the simplest case, right, which is in like undergraduate physics textbooks, how these eigenfunctions for one-dimensional Schrödinger operator decay exponentially, right? But this phenomenon is true for much more general potentials than simple like finite square wells, for instance. So a lot of research that was done in the last century was to try to extend these exponential decay results to much more general potentials. Um, and a critical result in this direction was the exponential decay results of Agmon, of small Agmon, um, where he gave like a new argument that allowed him to give exponential decay of eigenfunctions for very general potentials. Uh, so here I have in blue here is the sort of decay that Agmon obtains. It's an L2 exponential decay. It's called L2 because of, well, it's average, right? Like you're integrating, but what you're integrating an exponential function. So if this integral is finite, it must mean that the other function psi of x squared has to have some exponential decay. So that in that sense there is exponential decay. And okay, so this is a result of Agmon, and but you will notice here that there is this function rho, which is defined as a geodesic for this metric written here. The s squared is v minus e plus v minus e plus, which is the positive part of the difference between the potential and the energy, right? E is the energy of the eigenfunction. So then you are not, rho is not like distance in the Euclidean sense, but rather distance in this, with this weight, okay? And with this weight, they is able to obtain this exponential decay estimate. Now, the precise rate of decay of solutions is a very challenging problem, related to something called the Landis conjecture about the unique continuation of solutions. And so these questions of exponential decay do not only have to do with physics, but also with mathematics deeply. So now, okay, so then can we move to the next slide? Thank you. Thanks. Yes, sir. So now, on the other hand, other than eigenfunctions, the potentials will force the exponential decay of other solutions too. So another one, for instance, is the fundamental solution to the operator, right? So this is a solution to the problem L gamma equals delta. Well, delta is the Dirac delta, the point mass at y, and then and the fundamental solution satisfies this representation formula that you can write any Milgram solution to the problem by integration between the fundamental solution. So this is sometimes also called Green's representation formula for solutions, and it's very useful tool in the study of these elliptic PDEs. But also the decay of the fundamental solution is very interesting on its own, because it implies several properties that are useful in harmonic analysis, for instance. Okay, for example, if you have certain polynomial decay estimates for the fundamental solution, then you can show that certain Riesz transforms associated to these Schrödinger operators will have LP bounds. Okay, so for that reason, the decay of fundamental solution had been studied a while to be able to establish LP bounds for certain Riesz transforms. But then Michael Fries showed in 2 dimensions that the Green's function satisfies certain exponential decay estimate. It was very, very high and sharp in some situations. So then in 1992, Songwei Shen went on to prove the similar exponential decay estimates in 3 dimensions or more, right? 3 dimensions or higher. And under this condition that V is in a reverse Holder class. And what we have here is, we call this a sharp exponential decay bound on the fundamental solution. We call it sharp because you have this control both on the upper bound and on the lower bound by essentially the same function, right? Except that we are changing the exponent a little bit, because this epsilon1 on the left, epsilon2 on the right, and as such, it's it differs a bit, but the form of the decay is the same, right? And it's exponential because it's in terms of this Agmon distance, rho x by m squared. Now, but what is this m squared, right? So this will go into detail soon. Okay, so now we go to the next slide, please. Yeah. Thank you. So here M is what is called nowadays as the Fefferman-Phong Shen maximal function. Okay. Okay. And now there's no noise. Okay. So this function M has come to be known as the Fefferman-Phong Shen maximal function, and one it was introduced by Songwei Shen to study precisely these questions that I was saying about the Calderon-Sigmund operators and Riesz transforms. So oh no, thank you. So its definition is given here, but you shouldn't be scared about it. Well, it is a maximal function in the sense you're taking supremum over the radius that satisfy this property. But here I made a picture the sort of will give a more intuitive reasoning as to why this is an interesting function to study. If you're thinking that about Agmon distance, you want the distance between points that will see the effects of the potential V um, in terms of the equation, right? Now, in this picture, you have 2 points X and Y. And suppose that the potential V is identically 0 on this part, on this large part that connects X and Y, right? And then on this other brown part, V is much bigger than 1, okay? It's just very large. But on this white part, V is just identically 0. Then if you took the Agmon distance that Agmon takes, for example, the problem is that it collapses the points X and Y to the same point, right? The distance, the Agmon distance that Agmon used would tell you that the distance between X and Y is 0 because the potential is 0 in a path that connects X and Y. So using the potential by itself is not quite right. So the insight of Phong Shen was to use this maximal function, which brings in the information from around the points, and that takes in like the good amount of the potential that has to be used in equation, right? Or in other words, it works at the scale of the equation. So when you're looking to the distance with the Agmon weight given by this maximal function m, what m is doing is it's taking the values of v on these large balls, right? That we have drawn here, and so even though v is identically 0 on the path that connects x and y, it is not 0 on these balls around x and y, and therefore the distance will not be 0. It will actually be very coercive, right? The point will be very separated under this new Agmon distance. Okay, so next slide. So now this is useful. This maximal function is useful when the potential is in a reverse Holder class. So that it moved to previous. Okay, thank you. So it's useful when the potential is in a reverse Holder class. And now, what does it mean to be in reverse Holder class? This is a class of functions that has become popular around the 70s or 80s of last century because of its connection to harmonic analysis and the Munkenhaupt AP weights. So what does it mean for a function to be in a reverse Holder class? It means that you have the function satisfies a reverse of the Holder inequality. So you have Holder inequality here first, and it is, the classical result from real analysis. So we will say that the function is in reverse Holder class of exponent p if you can do the other direction, right, of the inequality with some constant, okay, with some constant c. And if you can do this for every ball, okay, for every open ball B, if you can do this, then we say that the function is in the reverse Holder class. This is related, as I said, to the Munkenhaupt P ways because the union of all of these reverse Holder classes is the same as the A infinity, as the space A infinity. Now, okay, so then examples of these include the positive polynomials. So that's can you go? Okay, yes, the positive polynomial or the powers of x, right? So the x magnitude of x to power alpha, where alpha is some, for instance, some number bigger than -2, for example, then your potentials will be in a certain reverse Holder classes. Okay, so the reverse Holder functions can have singularities, right? They can have singularities. They don't have to be essentially bounded. Now, non-examples of these functions include exponential weights, that is either weights that increase exponentially or also that decrease exponentially, right? Positive weights that decrease exponentially. They are non-examples. The reason they're not examples is because reverse Holder weights must be doubling. Okay, they must be doubling, but exponential weights are not doubling. And other types of non-examples include random variables. Okay, so functions whose values are given by random variables in some way, then they will not satisfy reverse Holder inequality almost surely. So this is the one thing that the Fefferman function maximal function is very useful to study these potentials when they are reverse Holder weights, but it is not useful to study Anderson localization, which is a phenomenon that occurs for random potentials. Okay. So in the next slide, can you click twice, please? Another time. Okay, thank you. So in this slide, we see why. Why is this function? Okay, I told you like a picture, but mathematically, why is this function useful to study exponential decay? And the reason is because of these so-called uncertainty principles. So the way that Abman proved his exponential decay result initially was by simply observing this trivial inequality, okay, that you can bound the potential energy with V by the kinetic plus the potential energy. Right? This inequality is trivial because because this kinetic energy term is non-negative, so you can just throw it out and you get this inequality. So even though it's a trivial inequality, it's still from this inequality you can obtain a lot of information if you know that your potential is good. Okay, if it doesn't degenerate too much. Okay, so it was used very powerfully by Agmon with his argument, able to give exponential decay. Now, the reason why you want this kind of inequality is because you are able to bound the kinetic and the potential energy bounded below by a single potential energy, right? So the main point is to bound the energy of the system bounded below by a potential energy. So Agmon did it with the trivial estimate, but there is more subtle estimate, and eventually Fefferman and Phong proved what has come to be known as the Fefferman-Phong inequality. And one variant of it is the one that Shen proved, which is written here. And this inequality, which is more difficult than the previous one, but the point is that still you are bounding the energy of the system below by this potential energy, except that now you have replaced V by M squared. Okay, so M squared is taking place of V, and it somehow is taking in much more information than if you just put V there. Okay, so the next slide, please. Thank you. Yeah. So now, Shen did this for the operator minus Laplace plus V. But now you can easily ask if you can do this for other operators, right? Like, what about the operators, the Schrödinger operators in non-homogeneous media, which are of the form minus d per graph plus V, and A is a not necessarily symmetric matrix, elliptic matrix of bounded measurable coefficients. Okay, the ellipticity condition is there. It's sort of a uniform positive definiteness of the matrix, right? And the boundedness too. So yes, when A is not symmetric, we also want to ask the same questions. Then the operator is not self-adjoint. It becomes much more difficult to get some of these results. But then other than this, you can also ask, what about the magnetic Schrödinger operator? Does the fundamental solution for the magnetic Schrödinger operator experience exponential decay as well? Magnetic Schrödinger operator is much more subtle because its solutions are complex valued in principle. So you cannot just it becomes more difficult. In it does not have many properties like the Georgi-Nash-Moser estimates or Harnack inequality, for instance. Still, you will be able to control these solutions in a different way because it satisfies other principles. So it becomes it becomes interesting to see if you can prove exponential decay in this setting too. Then also, of course, other than fundamental solutions, you can ask if you have similar exponential decay for Lagrange solutions or for resolvents of the operators. Okay. And now, thank you. Thank you. And now we have the magnetic Schrödinger operator. Can you click once more, please? Yeah. So here's the definition. You have the magnetic Schrödinger operator defined in this way, and the boldface A here is what is called the magnetic potential, right? So this is a real valued vector function, and it gives you the magnetic presence, right, in the term. Now, however, there is, if you take the curl of this vector function, okay, which is defined in this way, you might say, well, curl only makes sense in 2 or 3 dimensions. But you can extend this to higher dimensions too by this formula, right? So it's just a matrix. And then this matrix, we call it the magnetic field. And actually, magnetic field is extremely important for the properties of the magnetic Schrödinger operator. The reason is as follows. You have a gauge invariance, this property called gauge invariance. And what it means is that if you were to add the gradient of any smooth function to the magnetic potential, right? So A tilde is A plus gradient of phi, and phi is smooth. Then you have not changed the magnetic field because the curl of the gradient is 0. So even though you have changed the magnetic potential and you have, phi here is arbitrary. You can have any gradient, right? But even though you have changed the magnetic potential, you have not changed the magnetic field. And furthermore, you have these identities here that relate the solutions to the equations via just some phase, change of phase. So you see here, you just need to multiply by e to the I phi. Our phi is the function with the gradient you added to the magnetic potential. And similarly with these magnetic gradients, I like to call them just because they behave like gradients. Well, they like more rigorously they're like connections. But again, they're given just by phase changes. So, okay, now in the next slide, I'll show you another more about this gauge invariance. Sudeshna, could you please go to the next slide? Thank you. Thank you. Yeah, so about the gauge invariance, a very important part of it is that the energy of the system is invariant with respect to these gauges, right? With respect to adding this gradient of phi, it doesn't change the energy of the system. So it does not depend actually on the magnetic potential. It depends only on the magnetic field. Okay? And for this reason, any hypothesis that you want to put on the operator, any quantitative hypothesis, you actually should put it on the magnetic field and not on the magnetic potential. Okay, so this is a very important thing to understand magnetic Schrödinger operator and why we will soon put the conditions that we put on our results. Okay, and now I think we're ready to state main results. So could you please move to the next slide? Thank you. So yeah, so the first thing we have here, I have considered, we consider with my advisor these generalized Schrödinger operators. A, there can be any not necessarily symmetric elliptic matrix of bounded measurable coefficients. Well, uppercase A, right? And boldface A is a magnetic potential, and then V, you just the electric potential. And we take this assumption. Now, the assumption that V plus B is in reverse Holder class, okay, that is sort of a natural assumption to make just because that's the assumption, so that the Fefferman-Phong maximal function will behave nicely, okay? But actually, we need to ask for two more assumptions, which are not so natural. And this is written here, that V is controlled by M, by the maximal function, and also that the gradient of the magnetic field is controlled by M. Okay, these are not natural assumptions. In particular, we are assuming that the gradient, that the magnetic field has a gradient, right? And in principle, you would want to consider this result for irregular magnetic gradients, which are not differentiable. So, however, why we have these conditions? Because for a while they have been needed in order to prove the Fefferman-Phong uncertainty principle in the case of the magnetic Schrödinger operator. So there is a whole like 6, 7, 8 articles in the literature, or even more, that I haven't seen, where these conditions are always written. Then they're written because this is the way the Fefferman-Phong uncertainty principle was proved. So I just want to emphasize why we take this assumption. Now, under this assumption, we can state the first main result, which is this Lax-Milgram, this exponential decay estimate in an L2 sense for Lax-Milgram solutions. So you can see here, written it here. It's sort of the estimate that you would expect, and it is in L2 sense similar as to the L2 estimates of Schmal-Lagman. Okay, and now, thank you. Yeah, so in this theorem, I stated it for Lax-Milgram, but by just some changes, it can also be stated for resolvents of the operator. And then, from a background, Bruno and Klein prove an exponential decay for resolvents, but they're using heavily that 1/t squared, which is, is the t is coming from the resolvent, again, from not being near the spectrum of the operator. But for us, we really wanted it with no dependence on 1/t squared, and that can only come about because of our hypothesis on the potential. Now, yes, so the estimate is a new estimate, and yes, a consequence of the assumptions on V and the magnetic field. And then from the resolvent estimate, you could also estimate functions of the operator, this f of L, for any holomorphic F. Okay, very well. So in the next theorem, thanks. And the next theorem, no. Next slide, please. Thank you. Yeah, so then we have here the exponential decay upper bound for the fundamental solution of the magnetic Schrödinger operator. But in this case, we no longer consider generalized ones. We have to restrict to the classical magnetic Schrödinger operator that is written here, minus Laplace minus IA squared plus B. The reason for this is that we heavily use the Kato-Simon inequality, which I will present soon. But as you can see, this is the generalization of the estimate of Shen to the case of the magnetic Schrödinger operator. Except that we only have the upper bound. It makes sense that we have upper bound, and the magnetic Schrödinger operator is complex valued. So whether there even is a lower bound, even for the magnitude, is not so clear. Right? So it's still an open question. So okay, and then in this theorem, we now restrict to just the Schrödinger operators with no magnetic field. Okay, so there are the form minus v big grad plus v, and we have this upper bound and lower bound exponential decay estimate for the fundamental solution. So notice that for these operators, we don't need to ask any smoothness of v. We just need to ask that v lies in reverse Holder class. So again, there is these questions about how to remove those conditions in the magnetic Schrödinger operator case. Okay, so then in the next slide, thank you. Yeah. So some discussion in these theorems. The existence of the fundamental solution is new in the natural context because it was not had not written before, had not been written, but under very minimal assumptions on the magnetic potential and the electric potential, we construct the fundamental solution and show that it's a weak solution, at least away from the diagonal. And as I said, there is this ingredient, the Kato-Simon inequality, which is stated here. It's an estimate that allows you to bound the solutions of the magnetic Schrödinger operator by solutions to Schrödinger operators with no magnetic field. So here, remember, we don't have Carnot inequality or in the techniques of the Georgi March-Moser to give essential boundedness does not work in this setting of magnetic Schrödinger operator. But you can still, for instance, get local boundedness because of this inequality. Okay, and then another instance of this inequality is what is called the diamagnetic inequality, which I have written here, which allows you to see that you cannot say that the gradient of a function equals its magnetic gradient, but you can give a lower bound for the magnetic gradient by the gradient of the absolute value of the function. This is the diamagnetic inequality. It's also very useful tool in the study of magnetic framework. Okay, now we're going to move on to the second part regarding the landscape function in Anderson localization. Thank you. So then, what's going on here? So you see, we proved these exponential decay estimates for reverse Holder potentials. However, it is known that if your potential has very random features, okay, if it is random, then it will still cause exponential decay of the eigenfunction. Okay, this phenomenon is called Anderson localization. For Anderson, pictured here, who first won Nobel Prize in physics for finding this out in the 60s. And then, so here's the thing. On the left side, you have this thing that looks like broken TV screen, right? When it's just static. But what it is, each black square is, on each black square, the potential, say, takes the value 1. And on the white part, on the white squares, the potential takes the value 0. All right? So this is a random potential, as you see. And now on the right side, what you have drawn is the eigenfunction, one with low energy, okay? One of the first eigenfunctions. And as you can see, the eigenfunction is localized. It's not spread out throughout the domain. Okay, it's localized to some specific region, which seems weird given that the potential had this random thing, and thus in principle it would kind of look similar everywhere in the domain, but that's not what happens, right? The eigenfunction localizes very sharply. Okay, and then in the bottom with this color series is like a different version of the same phenomenon, but in a cube in 3 dimensions. Okay, so then here now, what is this landscape function that I have talked about? I have mentioned a few times. It's a solution to the equation minus Laplace u plus vu equal 1, right? And the idea of studying this solution was introduced by Marcel Filoshin and Svilana Mivoroda. So as you see, it's just a solution to a PDE, okay? And now boundary conditions you can choose, okay? You can choose Dirichlet boundary conditions, Neumann boundary conditions, periodic boundary conditions. You can choose the one you want that will help you study the eigenfunctions that you want to study. Okay, so why is it useful? Because it predicts, you can use it reciprocal, 1 over u, okay? You take 1 over u, and it predicts the wells of localization of the eigenfunctions. So here's the picture with example. Your random potential is pictured here, same as before, same drawing. And then in this middle picture, what you have is you have drawn these contour sets of the function 1 over u, okay, at a certain energy level. And then in the last picture, you see this part with shadow, this part that sort of filled in. That what it actually represents is the values of an eigenfunction, that black part. And as you can see, that eigenfunction is localized to one of these wells of the function 1 over u. So you see, by just computing what 1 over u is, you can draw this map, which will tell you where the eigenfunctions will localize. So that is one of the powers of this landscape function, although there are many others, because it has also been used, for instance, to extend the while loop, to give like a stronger version of while loop. Now, in the next slide, we have another example in dimension 1. So again, here on the left side, you have a potential, which is random values between 0 and 4. Okay, so this function is crazy, right? But then you take on the right-hand side the drawing. The blue line represents 1 over u. That's the function 1 over u. Whereas the other lines of different colors represent the first few eigenfunctions of this operator in one dimension. So as you can see, the eigenfunctions, its values are completely within these wells. Now these are numerical results, right? What I'm showing you here is numerical results, and not so much mathematical in nature, but all of this was done very recently, and the mathematical study of the properties of the landscape function is still ongoing. And now I'm going to show you some new results that have been obtained. Okay, but before that, I tell you one thing about why it also is useful, and it comes back to the uncertainty principle. Recall the Fefferman-Phong inequality, which we use to obtain exponential decay in terms of the Fefferman-Phong Shen maximal function. Now, the landscape function actually verifies this conjugation on the bottom here. And as you can see, this is a stronger version of uncertainty principle. In some sense, it is like the best possible uncertainty principle, because what it means, as you can see, you can if you throw away the very first term in this equation, right? You can just throw it out because it's positive, no negative, right? Then this gives you an uncertainty principle. It allows you to control in a lower bound the kinetic and potential energy by a potential energy with 1 over u, okay, the reciprocal of the landscape function. So as you can see, so this is one main reason why the landscape function is so useful. to study the localization of eigenfunctions. But we must also note here that you can do this no matter if the potential is in reverse Holder class or not. As I said, the main reason why it's so interesting to study it is because of its application to Anderson localization, which necessarily deals with potentials given by random variables. Whereas the tool of the Fefferman-Phong Shen maximal function could not be used, have not been used for potential beyond reverse Holder classes, or also with some other, actually, you can do better than reverse Holder classes, but you cannot include random variables. Okay, and yet the question happens of the connection between these two. So we'll look at that soon. But the first theorem I want to show you here very quickly is that you can obtain exponential decay of the fundamental solutions and Green's functions in terms of the landscape function. So here you have written one such estimate. For instance, if B is in L infinity, you can give an upper bound for the Green's function in terms of an exponential of an Agmon distance with respect to U. Okay, there should be a minus sign there. Yeah. But okay. It's supposed to be exponential integration. There would be no use if I show that it's bounded by an exponential implicit function. Anyway, so, but I have shown this for V in L infinity, but you can get a similar, a bit more complicated, but you can get a similar estimate when V is in L1 log, right? Except the first will be different because here I'm using explicitly the upper bound on V. You can also get very close to decay estimates for resolving and Lax-Milgram solutions in this way. And importantly here is that even though the landscape function is the solution to this Schrödinger operator in omega, and say omega is bounded, you have Dirichlet boundary conditions, the estimate that I get is independent of the diameter of omega. And that means it extends, okay, to whole domain. It can extend to unbounded domain. So part of our response is to also extend the landscape function to unbounded domains, where it is not so easy to see that a solution exists to the problem LU equal 1. In fact, sometimes it doesn't exist. If your potential is too degenerate, for instance, if it is 0 outside of a bounded domain, then it will not exist. Okay, there will be no landscape function. Or in other words, it will exist, but it will be plus infinity everywhere, which is of no use. But under some very mild decay conditions, it will it will exist. Okay, thank you so much. Yeah, now we go to the next slide. Thank you. So now, as I said, you have these two tools, the Shen maximal function and the landscape function of Deleuze-Meillard. And both of them use to study exponential decay. Now, what is the relationship between them? So for a while, this was open question because we didn't know how to really make them work. But in the recent, in my recent work, I saw that actually, when the maximal function is well defined, okay, and when you have some good properties, right? So for instance, in this reverse Holder class, then these functions are pointwise comparable. And so I show that 1 over U is like M squared. Okay, in this precise sense, it has this upper and lower bound with a uniform constant C. So this theorem shows that this new tool of the landscape function is in some sense a generalization of the Fefferman-Phong Shen maximal function that has been used for so long. But also, not only does it generalize it, but in some sense it also regularizes it. Because, for instance, if B is essentially bounded, then U is a locally Holder continuous function. So, generalizing this idea and also regularizing it, smoothing it a little bit. Okay, and now part of our last theorem, in the final slide, I think. Thank you, Sudeshna. Yeah. So now we show an application of this result, which is a new application concerning magnetic Schrödinger operator. So here, we go back to magnetic Schrödinger operator, and what we can do now is we can construct a landscape function for the magnetic Schrödinger operator, which itself was an open problem in our research group because it was not clear what to take. Okay, if you just take L to be the magnetic Schrödinger operator and you write LU equal 1, which they can do, right? But that solution will not give you good properties, is the problem. It will not give you the uncertainty principle, which is like at the heart of this thing. So is there a landscape function for magnetic Schrödinger operator? That was open, but now I can construct this landscape function for a magnetic Schrödinger operator using the ideas that I have shown you before. And actually, it is like, from the previous theorem, it is like the Fefferman-Phong Shen maximal function with the magnetic field in there. But now here's the thing, though. I need new conditions to state this theorem. My condition is this. You have the reverse order inequality, which is the natural condition you want to make so that the Shen maximal function will work, okay? But now I have a sign condition. It's the second condition here. It is a sign condition on the magnetic field. Okay, what it means, this condition, is that the magnetic field is, in some sense, pointing in a single direction or in a single half space. Okay, it cannot change signs. Or if it changes signs, it better cancel out with the electric potential or with the other components of the magnetic field. That is this condition. Now you might say that's like a weird condition because magnetic field is a matrix. You have a whole bunch of components. What does it mean to take signs? Well, another example I give is in 2 dimensions, for instance, the magnetic field is given by a single function, a real valued function B, okay? And in 2 dimensions, my sign condition would just say that the magnetic field does not change sign over the domain, for example, or rather that's an example of the condition. In 3 dimensions, the magnetic field can be represented by 3 functions, because there is just the curl of the potential A, and then this is just multivariable calculus, right? So you have 3 functions that represent the magnetic field. And then what my sign condition is saying is that these 3 functions must lie, like the values of it, must lie in a single octant in 3 dimensions, okay? In a single octant in 3-dimensional space. So in some sense, it's telling you magnetic field is only pointing in one direction. It's not really changing too much. Now, under those assumptions, I can obtain, I wrote here, for instance, the same exponential decay estimate that I wrote before. But what is the kicker here? The kicker is that I am no longer assuming that the smoothness of the magnetic field, which is those unnatural conditions I said before that were put on the magnetic field in order to make sense of the uncertainty principle. Now I can trade that smoothness assumption with this sign assumption. And moreover, my sign assumption is natural in the following sense. It generalizes sign assumptions that have been considered already in 2 dimensions. But here I am stating this in any number of dimensions above 2 or above. The magnetic Schrödinger operator, as a remark, does not really make sense in dimension 1 because of the gauge invariance. You can always gauge it out, and then it just becomes the usual Schrödinger operator. Okay, so that is all. Thank you very much for listening. And I'm sorry about the technical issue that I could not share my screen. I deeply thank you, Sudeshna, for helping me with the presentation.
So, any questions?
Oh, I would just like to make quick remark that these last few results that I mentioned will be put on archive very soon. I'm just finishing to write it on computer, but the results are done. Mhm.
So, let's thank the speaker again. And if there are no questions or comments, it was a wonderful talk, Dr. Poggi, and hope you will come back at our colloquium again. It was very fascinating.
Yeah,
And
thank you very much. And I would love that. And hopefully next time I'll fix this issue of Google.
you'll be more tech savvy. I'm also not a tech savvy person, but that's fine. So we all enjoyed the talk. And so we have more talks next week, Friday. So Stefan will send all the announcements. He's not here today. He's attending a conference, actually chairing a session. So I'll see everyone next week. Everyone stay safe and stay well. And Dr. Poggi, Bruno, my heartfelt thanks to you.
Thank you, Sudhir.
Wonderful talk, Bruno. Wonderful talk. And
Thank
kudos to
you.
Sudeshna, who is organizing exposure to different branches of mathematics for our students and people like us also.
Yes,
Oh,
I think,
thank you. Yeah.
Ajit, I think that's very important that we all get to know about different branches rather than
Yes.
just limiting ourselves to what we do. Thank you all.
Thank you.
Thank
Thank
you very much. Thank you.
Thank you,
Bye.
Maria.
Bye,
Bye.
everyone.
Bye, Pooji.